All right, so today I thought I'd start off with just a couple of closures on the two algorithms that we were looking at last week. The closest pair revisited. Remember that we were looking at a divide and conquer solution that exploited geometry. Um, Over the weekend, I mentioned an idea that I had on. Well, what if you did this idea, but without having to divide and conquer? And so I went ahead and programmed it, and I'll show it to you here in a second. But the idea here is to take this idea that you can go ahead and just take a point and then draw a limit, a line by, say, just take the first 2 points that you find, right? That defines a minimum distance. And then from every point, you only have to look forward, right? You only have to look forward a distance d in the x direction. And then you can limit it in the y direction as well with a distance of d. And so what I ended up doing is saying, well, what if we take that idea and instead of dividing it and conquering it, we divide it and conquer the other way. So if you remember in your Python exercises, there were a couple of ways of doing divide and conquer. You could divide it in half, right? You could divide something in half and then take the left partition and then the right partition separately. Or another way that you could do it is by dividing it into one, right? So for example, if you had an array like this and you wanted to sum them up, right? What you could do is you could say, well, I don't know how to sum up n things, but I know how to sum up this guy, A, plus whatever the sum of the remaining things are, right? So if this is index I, then the sum of I plus 1 through n. Right? In other words, you divided it not in half, but you divided it one by one. Now take that idea and take this idea and combine them. So what I mean by that is, take the first 2 points and establish a minimum distance, right? And then sort all the points in the x direction, right? Sorted with respect to x. And then for each point here, right, then you do the exact same trick that you did before of limiting this slice, and then you limit the in the y direction, right? And then you move forward to the next point, and you do that again, limiting this slice. And each time you find a new one, the slice gets smaller and smaller, right? The slice both in the x direction and in the y direction gets smaller and smaller and smaller. So you are cutting down the work as you move along here. Now, in the worst case, I do think that this is still going to be order n squared. But in practice, it's going to be just as good as the divide and conquer method. That was my theory anyway. And so what I did is I went ahead and set up an experiment here. First of all, I implemented the brute force and I compared it to my other two solutions to make sure that it works. And I'm testing this on a small number of points, only 100 points here. I do that one. I do the I just called this adaptive because this slice that you end up considering, it gets smaller and smaller and smaller as you find closer and closer points. It gets smaller and smaller here, and it gets smaller and smaller here. And then I called that adaptive. And then I put closest pair divide and conquer, which is just the straight up algorithm that I showed you, that you divide it into two sets, find the two closest points here, and then you have to look across the line. All right? I measured this in two ways. First of all, the number of distance calls, I'm counting that, and I reset that each time. And then I'm also timing it with respect to Python here. Python is single-threaded, so there's no multi-threading here. So this is all very comparable. I also make sure that I start with a fresh copy of all the random points for each algorithm here. Let's go ahead and go into that closest pair. You'll note here that they're in another file. I'm not going to show those to you because, of course, that's your programming for this Friday. But let's go ahead and take a look. And first of all, let's make sure that it actually works. And by making sure that it actually works, I mean, if I run all three of these algorithms, I should get the same answer. Right? Python closest pair demo. Right. Oops. Oh, where did I type the ls? Find ls. Okay. Line 30. There we go. There. Save that. All right. There we go. All right. So there's the algorithm. There's the brute force algorithm. It took 4,951 calls, distance calls, which makes sense because 100 choose 2 is 4,950, and then we make one additional call from the answer here, right? The Euclidean distance here. And we got a distance of about 11,202. Right? And that's the exact same distance in the other two calls. So I'm reasonably sure if I ran this multiple times on different inputs, on different randomly generated inputs, all three of these are reporting the same distance. So that's a way that you can test your solution. Generate random points, 100 random points. That is completely feasible to run it on the brute force solution. You'll get your answer, and then compare it to your implementation of your divide and conquer strategy. Right? Obviously, and then I'm also timing it here. So on small number of points, they're all pretty comparable. But when we start getting up into, say, 1,000 points, right? Let's clear this out. Right? Now it becomes a little bit more noticeable, right? The brute force solution here was taking almost a quarter of a second, while the other two are still relatively in a blink of an eye. Yeah?
Why is, I think the adapter's making less calls.
It's making fewer calls, right?
It's taking more time.
Yeah. So what's going on there? Let's think about that here in a second. But I want to make sure, again, it's correct. And we're starting to see that there's a slowdown here. If I go up to, say, 10,000, right, then I'm going to have a quadratic blow up here. So in other words, 10 times more, that's 100 times slower, roughly. And if it was a quarter second before, that's going to be 25 seconds now, right? Or thereabouts. And it ran first, so that's what we're waiting on here. And you'll see the other two are still in a blink of an eye, relatively, right? While we're waiting on that, I did go up to, well, I estimated up to 1 million points. And the divide and conquer strategy here will take 3.5, or the brute force, excuse me, will take 3.2 days, based on my extrapolations. There we go. It was about 31 seconds. What did I say? 25 seconds? So we're in the ballpark there. And using that and extrapolating, I said, well, if I went up to a 1 million, and note here that I think that I do have 1 million or 10 million and the greater. So you will have to, you cannot take 3.5 days here to solve that problem. But the other two were very, very comparable. 32 seconds for the adaptive and 24 seconds for the non-adaptive, the straight up divide and conquer strategy. So now your question of, well, it seems that the adaptive strategy here is always going to have fewer numbers of distance calls. That's true. But that's not where the majority of your actual time is spent. The majority of your actual time is spent in creating those slices and sorting those slices, right? And then taking those slices and sorting them with respect to y, so that you can do binary search, right? And that's what ends up being most expensive. To try to speed it up, I did change the adaptive so that it's not just taking the first 2 points to establish that minimum distance. What I did is I took the first 100 points and I ran the brute force strategy on it. And so that establishes an even smaller distance up front before you even start. Still, I could not find a crossover point where it beat it out here as far as time goes. As far as number of distance calls and computations, it always beats it. But as far as pure time goes, it never beat it. So there's where the engineering hat comes in, right? When you analyze an algorithm, you get this big O analysis, right? And it would come out to be, well, in worst case, it's going to be order n squared. But if your real measure of complexity is going to be the number of distance calls, then this one, the adaptive, turns out to be even faster, right? In practice. But that's not our bottleneck as far as real time goes. Our bottleneck as far as real time, at least as far as Python goes, is creating those slices and those sublists and those sub arrays. Right? And I could never get it to beat it. I imagine that the reason that the time here is much less is because you are doing fewer of those slice computations, right? That the real cost here is not the distance computation, but creating those slices, right? And those subsets. Right? So there's my solution. I look forward to seeing your solutions. If you want to take my adaptive idea and implement it that way, that's fine. Again, as long as it runs in a matter of minutes or seconds, hopefully, rather than days, because that ain't happening. Right? All right. Yeah, go ahead.
Is there a way to like, because the program times out in 5 minutes, but when you know you messed up, you have to wait 5 minutes to tell.
Well, I would do what I did here.
Oh.
I would create a bunch of random points. I'll show you that code if you want. There's nothing really there. Load points from a file. That's what you'll do with the actual file. But for testing purposes and for benchmarking, just create a random list of points. Test it locally, yeah. And then pump it up to 1 million. And if it does it in a matter of 1 minute, I think you're good to go. All right. The other thing that I wanted to wrap up was Karatsuba multiplication. So I did find that link finally, and lo and behold, it was written in C, right? Under the hood, everything is fast because it's written in C. And the cutoff was indeed 70 digits. There was a second cutoff for repeated squaring, which I think there was a different cutoff for that one. I think it was much higher because the threshold was much higher. But it goes back 20 years. I posted on Piazza the actual, this predates Git, so the pull request. The guy implemented Craig or something, whatever his name was, implemented a Karatsuba multiplication and put it into Python. And their threshold was to do it this way only if it's 70 or more digits. Otherwise, just use regular old multiplication. And of course, it was all written in C. It's very complex. But what I wanted to show you is last year I did it Karatsuba in Python itself, right? And you can find these all over the place. But basically what it does is it looks at the number of digits. Now, so this is base 10. And if either one is 0, of course, we return 0. If the number of digits is at most 1, then we just go ahead and go with regular multiplication here. Otherwise, we compute a power. Remember that this is 10 to the n divided by 2. And then we split them up into those two numbers, right? We had that somewhere in our notes here. There we go. There we are. So we split up these two large n-digit numbers here into a1 times 10 to the n divided by 2 plus a0, which is the lower order digits, higher order digits here. We did the same thing for b. And then we split those up into a1, b1 multiplied by 10 to the n, a1, b1, b0, and then we multiplied these together, and then we use that identity so that we could reuse those multiplications. Well, you take this multiplication right here, right, and reuse it over here. We'll take this multiplication over here and reuse it over here, and then all we have to do is compute the sum of these two things, and then compute one additional multiplication. And that's exactly what I do here, x, y, and z. Right? And then all we need to do is up the power again. Remember that we have to multiply it by 10 to the n right here. Then the inner part here multiplied by that power. Again, the entire thing right here multiplied by 10 to the n divided by 2. And then finally, the third thing over here. I benchmarked this before I came in. And as expected, you're not going to beat the native multiplication here, right? Because the native multiplication is written in C. My Karatsuba multiplication here is written in Python itself, which is then just an abstraction above the one written in C. So we can benchmark that really quick here if you want. Python Karatsuba. Here I'm generating a random digit of 1,000 digits, right? And there we go. So I also have a binary version here that does it not base 10, but base 2. And for that, everything is just a shift instead, right? Shift over, shift left, shift right. And I've got a binary version there. I'm getting these very, very large numbers, and I'm assured that they're all the same. Otherwise, it would have printed out error instead. So again, I'm checking my implementation with a known correct solution, the multiplication, right? And the binary, turns out, is always the worst, right? That's going to take way too long. Here's my Karatsuba base 10 multiplication. You can see that it's taking tens of thousands of times longer than just the native multiplication. Why? Because it's written in C, right? And you can up this There's 10,000. If I went up by an order of magnitude here, it would start taking 19 seconds for the binary version, 4 seconds for the base 10 version, but still, we're not even at anything noticeable for the native multiplication. So it was very interesting that they are using Karatsuba multiplication, but not at all unexpected that it's actually written in C. Right? You'll never beat that. Right? All right. So questions on those two? Otherwise, what we've started looking at is another way of doing matrix multiplication. So remind me just how we do matrix multiplication in general. Again, hopefully you've had linear algebra. If not, that's fine. Let's go ahead and go with a 3 by 3 matrix here. 2 by 2. A, B, C, D, and E, F, G, H. Oops. So if I want to multiply those two matrices together, what do? I take AB, and then I flip it. In fact, let me try this. A, B, copy, oops, undo, but I can go ahead and paste, right? And I flip it like that, and then what do I do with it? I multiply it by the first column. So I end up with, and then I sum those up. So AE plus BG. It's basically the dot product, yeah, but the vector has been transposed. So you're taking the row and then you're making it into a column, right? The next entry here would be the first row and then the second column. So A, F, B, H, right? And then for the next row down here, it would be CD times EG, CE plus DG. Correct me if I'm wrong on any of this. CF and then DH. Right? So there we go. For a 2 by 2 matrix, right? So in other words, n, the dimension here is going to be 2. Let's count up the number of multiplications we did, and let's count up the number of additions we did. So how many mults did I do? 8. Good. And how many additions did I do? 4. Right. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4 additions. Now think more generally here. What if I have an n by n matrix and another n by n matrix producing an n by n matrix over here? How many multiplications and how many additions would I end up doing now? Yeah. Right. Ultimately, it's good. How many nested loops though? Okay. For each entry, yes. Right. For each for each entry, it would be 2 for loops. Now, how many entries are there? N squared, right? Right. So actually, just one, right? It's just one for loop for the inner. So altogether, what is this going to end up being? Approximately n squared, but this one is going to run n times, n minus 1 times actually. So n cubed, approximately. All right, and that meets up with our expectations here. 2 to the third is going to be 8. So in general, the straightforward multiplication is going to be order n cubed multiplications and also n cubed additions, I believe. Yeah, well, because there's a -1 somewhere for additions. It's still going to be order n cubed, though, I believe. It's in terms of if it's an n by n matrix, matrices, right? So It's in terms of this one n right here. Not the, so our input size here, we're going to treat just one dimension as n. Right? If you want to, you can go ahead and say that the input size, question mark, n squared. If that's the case, right, then these change. You divide by n squared, and you get n to the 1.5, which is weird, right? And so forget about that. I'm thinking it is, but now, damn it. You know what? We'll come back to that. I'll leave that as a question mark here. All right. In any case, can we do better? So, like I was trying to say on Friday, or I guess it was Wednesday now, how did Karatsuba come up with that idea? Right? Well, he just wrote it out on a whiteboard or a blackboard back then, or a piece of paper or something where, you just try a bunch of things and then finally something occurs, right? And that's what Strassen did in 19-something, whatever. Let's see. Where's Strassen? There we go. Yeah. I think it ends up being n minus 1 times n minus 1 times n squared. Or n minus 1 times n squared is why I think it's still n cubed. But it doesn't matter. We're going to look at multiplications. Right? So again, Strassen is sitting there on his whiteboard or on his blackboard or something like that, and he's looking at a 2x2 matrix, and he's manipulating things and moving things around and applying identities and stuff like that, and he comes up with this, right? Where M1, that the first entry here can actually be done in terms of these 4 other values. The second entry can be done in terms of these two values, and then these 4 values over here, where each one of these values is defined in terms of the original entries over here in the other 2 matrices. Right? Now let's count. Now ultimately, what we said was for a 2x2 matrix here, we need 8 multiplications and 4 additions. For this identity that Strassen came up with, let's count up the number of multiplications and additions. So, what about multiplications? Well, that's why it's written like this. M1 through M7, there's only 1 multiplication for each one of these values. So there's 7 multiplications instead of 8. Okay? What about number of additions? Understanding that a subtraction is an addition, right? A subtraction is an addition by a negative number. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that all? To actually get the values that you need are going to be more. 11, 12, 13, 14, 15, 16, 17, 18. Right? So it looks on the surface that, well, we might be doing more work here, right? Because instead of just doing 4 additions, we've blown that up to 18 additions. But we have saved from 8 additions or 8 multiplications down to only 7. Right? Is that a savings? Right? Well, if your elementary operation is multiplications, absolutely, you get away with 1 more, ignoring additions. If your elementary operation is additions, no, you didn't buy anything. You blew up your work. Yeah.
Isn't multiplication more expensive?
Yeah. So which one of these is more expensive in real life on a computer? Definitely multiplications, right? So you might think even from an engineering point of view, we're saving a lot here, right? Yeah, we're paying for it with respect to a number of additions, but we're saving a lot here. Now what you can do is you can generalize this, right? So I'll just bring this over here. That it doesn't just work on a 2x2 matrix. It works on any n by n matrix that you can come up with. All you have to do is split it up into 4 quadrants. If you split it up into 4 quadrants, these values then just become, instead of scalars, they became submatrices. So for example, if you had this big, 64 by 64 matrix, right? You would split that up into into 4 submatrices. Each, how big? 32 by 32, 32 by 32, right? Now each one of these can be split up further. 32 and 32, if you split that up into 4, you get 16 by 16. Right? So when do you stop? When you get down to 2 by 2, or you get down to some threshold cutoff point that we've been incorporating into all of these algorithms. 70 digits for Karatsuba multiplication. 100 points for the closest pair. Once you get down far enough where the recursion no longer pays off, then you stop and you use whatever brute force method you want. Right? So, from a theoretical point of view, does this bias anything? What I'm going to say here is let m sub n be the number of multiplications by Strassen on an n by n matrices on 2 n by n matrices. Okay, we're only looking at 2 right now. All right. Well, obviously we're making a recursive call on matrices how big. If I go from 64 down to 32, if I go from 32 down to 16, 16 down to 8, 8 down to 4, 8, and 4 down to 2, n divided by 2, exactly. Right? How many of them are, how many recursive calls am I making? To do multiplication, I need 7 values. Right? I need 7 matrices. So I am making 7 recursive calls. Right? Now, how much non-recursive work am I doing? Let's go back over here. Here's some non-recursive work. Right? All these things for additions is non-recursive work. All these things to put it all together is non-recursive work. But does it matter? Those are all additions. This is where I'm cheating, right? The master theorem allows me to say that there were 0 non-recursive multiplications, right? Yeah, which is a constant, yeah. Because what is m? Again, it's the number of multiplications by Strassen, not the number of additions, right? So, master theorem, a is 7, b is 2, and d, our exponent, is going to be 0 because this is a constant. All right? Now there is a base case where you do, that's where you end up doing non-recursive multiplications, but it's only in the base case, and that doesn't matter for the master theorem. Remember what the master theorem says in this case. 7 versus 2 to the 0. 7 is greater, so case 1 applies. Does anybody have that off the top of their head? Otherwise, we'll go ahead and find. Where is it? Yeah, it's one of the log ones. Where's... Oh, no. Do I not have master theorem anymore? I'm sure I have it in computer science, too. There we go. There we go. Yeah, it is. It is. There's the third... sorry, not case 1. Case 3. And so it's going to be order n to the log base b of a, which is equal to n to the log base 2 of 7, which is less than n to the third. Right? It's going to be like 2 point something. I have it somewhere. There, 2.807. So altogether, that's order n to the 2.807 and change, because of course it's an irrational number, right? Versus order n cubed. Is there a speed up? Yes. In fact, there's even a speed up in additions, right? All you have to do is set up the same recurrence for a number of additions. You do how many? You do actually 0 recursive multiplications, right, on inputs that are half as big, and then you do end up doing 18. Right? Actually, no, sorry, you do have to quantify the recursion, because you are doing additions in the recursions, right? So again, you have 7 versus 2 to the what? Again, this is constant. So this will end up being 0. And again, the case 3 implies that the number of number of additions is going to be order n to the 2.807 and change, or whatever it was. 807? Yeah, 807 and change. Right. So according to the master theorem, you are winning on both additions and multiplications. Now, do you think if you actually were to do this in practice, you'd be winning? Only on very, very, very large matrices. And do you think that if you actually did this in Python, you'd ever be winning? No. If you did it in C, there's some speed up there. Right? Say what? You lost with respect to efficiency, most definitely, when you chose to use Python. Now, arguably ease of use, maybe, I don't know. Right? I still don't understand people that advocate for Python for the first language, because every argument that they've ever come up with always has a counterexample of, well, this language does it even better, and also you're just trading one bad thing for a different bad thing, right? As far as, people that are learning, beginning to learn programming. Say what? Yeah, I mean, first of all, dynamic programming languages, dynamically typed programming languages should not be your first language. There should be rules, right? Programming language that relies on white space for its blocking should not be your first programming language. You should learn good style up front that is enforced with actual syntactical rules. At least that's my take on it. But in any case, no, you're never going to. If you started programming this stuff, you're never going to find a better way of doing it, unless it's for huge matrices, and then there are better heuristics anyway for that. If you're interested, other people have come up with other identities by moving things around. Again, whiteboarding stuff, blackboarding stuff, and they've come up with other ways of and other identities. The fastest one is, of course, Winogard. And I'm not going to show you the identities or anything like that, but he improved it to order n to the 2.3727, or not 27, but 3.754 ... And then Williams came along, and the exact same algorithm, but she made a better analysis of it and took it down to 2.3727, right? Which was considered huge. Look at that. You're talking about taking it down only 2/100ths of points in the exponent, and that took a Herculean effort as far as mathematics goes. And it was just an analysis of that improved it. To my knowledge, this is still the best. What is theoretic best? You have to look at the input. So you have to look at all the entries at least once, right? That's a trivial lower bound, right, on general matrices. So there is a huge gap from here down to here, right? Can we do better? Who knows, right? Just like, can we do better multiplication? Well, they started out with the grade school method, order n squared. Karatsuba cut that down to 1.5. Toom Cook and the fast Fourier transform took it down even further to almost linear here. And then finally, in 2019, they reached optimality with order n log n. There is a lower bound argument, I believe, that you can make for multiplication. You have to look at all the bits, right? If you don't look at all the bits, if you don't look at all the digits, how can you get a correct answer, right? And so there's a trivial lower bound of order n, right? But then there's also this other lower bound of order n log n. Yeah.
So optimality is like things to theoretical.
Yep. Algorithms give you an upper bound, right? Big O analysis. Mathematics will say there's a lower bound on this. This is the bare minimum that you can get by with theoretically, right? And once you've closed that gap, that's when you've hit they've met in the middle there. Then that's reaching optimality. You can't do better. Right? Now you might come up with another algorithm that achieves optimality but has different properties, but optimality is as far as you can get. Sometimes I've had people implement as an exercise Strassen's matrix multiplication. It's not that difficult. I mean, look at Karatsuba. Karatsuba seemed difficult, but there it is. That's it, right? All you have to do is translate the pseudocode and you're good. But there are some gotchas, right? What if you don't have square matrices? Right? What if your matrices are not nice powers of 2? Remember, because we're cutting it in half each time, right? The solution to both of these is pad them out with zeros. And what I mean by that is all you have to do is, if you don't have a square matrix, if you instead you have this rectangular matrix, and to pad it out would mean that you make it square by putting a bunch of zeros there, right? And if you've got this other matrix here that looks like this and this, you pad it out with zeros. Right? And then when you do matrix multiplication and you get this smaller matrix here, there's where your answer is. And guess what? Because everything is padded out with zeros, all these are going to be 0. And so all you have to do is cut them out at the end, right? And you've achieved it without having to worry about those. Well, if it's not divisible by 2, if it's not a power of 2, if it's not a square matrix. This works for any matrix multiplication. It doesn't have to be square. Right? All right. Any questions on that? All right. So hopefully you've seen matrix multiplication before, but hopefully also you've seen linear algebra before. And what I mean by that, you've certainly seen linear algebra before as far as, where's my system? I want a very simple system. As far as, say, this goes. This is something that you would see in, say, 8th, 9th grade. 3x plus 2y is equal to 35. X plus 3y equals 27. This is a system of linear equations, right? Y linear, well, x, it's not x squared. Y, it's not y cubed, right? They're all linear. And it has 2 unknowns, x and y. And we have 2 equations. Because we have 2 unknowns and 2 equations, we can solve this potentially. How would we go about doing this if we were back in 8th grade? Oh, okay. No. If we were in 8th grade.
X equals,
Yeah. So take the second one here, right? And just take y onto the other side, right? We'll solve for x is equal to 27 minus 3y. Right? Take that and plug it in up here. And you'll get 3 times 27 minus 3y plus 2y is equal to 35. There's one equation with one unknown. And now it's just algebra. What would it be? 9, 7, so minus 7y is equal to 3 times 27, 81. And then take it out and do the other side. 35 minus 81. And then all divided by negative 7. That's y. What is it? Okay, whatever it is, right? That's what. And then what would we do with that value? We would plug that back into one of the other equations, which would make this into a constant, and then we've got then we can take it onto the other side and solve for x. That's not how they taught it in 8th grade.
I feel like when I was taught it, our teacher basically said, here's substitution, here's elimination.
Okay, there's the key word. They started you off with Gaussian elimination, right? Gaussian elimination, for example, for 3 variables, right? So here's a system of linear equations. X minus 2y plus z is equal to 0. I'm just pulling this one off as an example because it probably comes out to nice whole numbers. Plus y minus 3z is equal to 5. Plus, and then another one is 4x minus 7y plus z is equal to negative 1. Right? Now we have 3 equations and 3 unknowns. These are all linear systems. You might, in general, have n unknowns, that is, variables. If you have n unknowns, you need at least n equations. Why? What if I gave you x plus 2y is equal to 3? Does that have a solution? Yeah, it has an infinite number of solutions. Why? Get this into a normal form. Take x onto the other side and divide by 2, and you've got negative 1/2 x plus 3/2. There we go. It's a line, exactly. And how many points on that line? I don't know. No, it's going to have slope downwards, right? Half slope downwards, and then the y-intercept here is going to be right above here, so it's going to look like this, something, right? Off to infinity, off to infinity. Every point on that line is going to satisfy this equation, right? So what does it mean when we start out with 2 equations here? We have 2 lines, right? Now, how many points lie on this line and on this line? 1, their intersection point, right? That's how you visualize it in 2 space. What does it look like if you have 3 equations and 3 unknowns? You don't have lines anymore. You have planes. 2 planes intersect at a line. 3 planes intersect at a point, and that gives you your unique solution. Right? What does it look like when you have 4 unknowns and 4 equations? Can anybody tell me that? No. Yeah, okay. You just passed the human test, right? Nobody can visualize that. Why? Because we're 3-dimensional beings, right? You can't picture 4 space, higher dimensional spaces. You can picture projections of higher dimensional space onto our dimensions, right? That's where you get the tesseract, right, from Marvel movies, right? It's just the cube within a cube. It's all the points are connected on the corners, right? That's what a 4-dimensional cube looks like when it's been projected down onto 3 space, right? Just like if you take a 3-dimensional cube and project it down onto 2 space, onto this flat surface right here, that 3-dimensional cube becomes a what? A square, right? So the same idea there. There's no way to nicely to visualize this stuff. So instead, we have to think about them more generally, right? How would we go about solving this? Now go to your 8th grade teacher who immediately jumped to Gaussian elimination. What do? You start eliminating things, right? I want to get it to look like this diagonal here. Because what if I had a system that looked like that from the start, right? So 3x plus 4y minus 7z is equal to 32. And then I don't have an x over here at all. Instead, I have 8y plus 3z is equal to 25. Right? And then my third equation here will just be z. 4z is equal to 16. Right? What about the coefficient? What about this term? What about this term? What about this term? They're there. It's just that their coefficients are 0x and 0y. Now, why is this beneficial to me? What if I can get this to look diagonally from the start here? This is called echelon form or reduced echelon form, right? That it looks like a triangle of zeros over here. Yeah, how do you solve the system now? Yeah, z is 16 divided by 4 equals 4. Plug that in here. What do you get now? One system, one equation. Right? Take this over to the other side, divide by 8, and you're done. Well, now that you've solved z and y, plug those in there, and you've got one system, one equation, one unknown, and do the same trick. Right? The key is to get it into this reduced row echelon form to begin with. And to do that, we're going to use Gaussian elimination. To get a Gaussian elimination, we need to understand what are some valid things that we can do to this. Right? So let's go over here to this one. What can we do to this without changing the system? What could you do to this one without changing the value of the system? Valid operations. Oh, what are the three fundamental ones?
Row operations.
All right, yeah, you can multiply
Yeah, you can add
a row by a scalar. Not 0, though. What if you multiplied a row by a 0? 0 is equal to 0. Wow. You just found a fundamental theorem. 0 is equal to 0. Good job. So don't multiply it by 0. You can multiply it by small values, 1/2, to eliminate things and make things ones, right? You can add or subtract one row from another. Right? Yep, and then you can do these two in conjunction with each other. What else can you do? You can swap rows. Right? Why? Because there's nothing special about me writing this one first versus this one first. They're the same equations. Can you swap columns?
that makes it change.
Yeah, it changes the variables. You can do that, well, as long as you keep track of it. X becomes Y, Y becomes X. And then you need to keep track of all of those swaps. Right? What else can you do? You can add a scalar to a row. Can you? Oh, on both sides, right?
Like, you can multiply this one by 2 and then add it to
That's kind of these two in combination. But you can add like +5 on the left-hand side, +5 on the right-hand side. That doesn't change anything. It's not that useful. But there are, that's why I was surprised when you said the 3 fundamental operations. There are a couple, like a dozen operations that are valid, but not necessarily useful. Right? Yeah, these are the 3 that we're going to use. 1, 2, and 3. And so we'll codify all of that next time with some pseudocode. And then you'll ultimately program it as well. But that's the pseudocode that I'm going to present. It's pretty much just a one-to-one translation over, and you're done. All right. I'll see you on Wednesday then.